Hello everyone. In this video, we will finish discussing how to deploy a feed-forward neural network on an Arctic 7 FPGA. What you are seeing right now is the end result of this. Images of numbers are sent from a computer to an FPGA using UART. The FPGA receives these images and then makes a classification using the neural network. In this video, we will review the two Verilog modules previously discussed. These two modules were the layer calculator module and the pulse generator module. Once we have finished the review, I will show you how the entire feed-forward neural network is implemented and connected to a computer using a custom UART controller. If you have not watched the previous videos, then I highly recommend watching those first before continuing with this video. Before we continue, I want to quickly mention the mission behind this channel. The long-term goal is to turn TrueSight Labs into a non-profit organization focused on digital design and hardware engineering, so that motivated people can go from knowing nothing to being an expert in the shortest time possible. If you want to build your skills while simultaneously pushing that mission forward, you can support the mission by purchasing the book. The description includes an Amazon link for the physical copy and a Stripe link for the digital copy. The book is priced similarly to what a typical high-end university textbook would cost, and purchasing it grants you full access to all future course updates. Alright, so now let's get started. To summarize, the entire purpose of this AI video series was to show how to implement the network shown below in Verilog. This network, while simple, was able to classify images from the MNIST dataset with flawless accuracy. There are 3 layers in this network. The first layer has 30 neurons, the second layer has 20 neurons, and the last layer has 10 neurons. To review the Verilog modules discussed in the previous videos, it's best to show how these two modules can be used to implement the first layer of our neural network. The diagram to the right shows the 2 main ways of representing the first layer. On the left side of the equal sign, we have the block diagram form. On the right-hand side, we have the detailed form where each neuron is shown. So to implement this layer of 30 neurons using our previously discussed modules, there are only 3 main challenges to address. The first is how to store the weights vectors, the biases, and the input vector. The second challenge is how to design the address generators. The third challenge is in figuring out what sequences need to be applied. Alright, so this is the layer calculator module from the last video. The Verilog code for this module has already been discussed, so it will not be covered again. The first challenge of making this module implement the first layer is in choosing how the memory is formatted. Before we can know how to format the 3 memory units, we must first review what is going to even be stored in the memory in the first place. In layer 1, there are 30 neurons. Each neuron has its own distinct weights vector and bias. For example, neuron 0 has its own weights vector and bias, neuron 1 has its own weights vector and bias, and so do all of the other neurons. So how do you think we're going to store the X vector in RAM? Remember that there are 784 elements in the X vector, and that the same X vector is used for all neurons in the layer. If you're ambitious, pause the video and think about it yourself. Well, to store the X vector in memory, we would store it like this. Since there are 784 elements, we can store elements 0 at address 0. We can store element 1 at address 1. We can store element 2 at address 2. This basic storage policy can be used to store all elements within the X vector. Now what about the weights vectors? How do you think those will be stored in memory? If you're ambitious, go ahead and pause the video to think about it yourself. Well, the weights vectors would be stored like this. Each weights vector gets stored after the other. Since each weights vector has 784 elements, each one occupies 784 locations. Now what about the biases? How do you think those will be stored in memory? If you're ambitious, go ahead and pause the video to think about it yourself. Well, each neuron has only one bias, so we can simply store all biases like this. The bias for neuron 0 goes at address 0. the bias for neuron 1 goes at address 1, and so on. So we have now answered the first problem, but it's now time to discuss how the second one will be answered, which is how the address generators cycle through memory. Fortunately, this process is actually quite simple, due to the smart way that we chose to map the data in memory. The XRAM pointer repeats from 0 to 783. The WROM pointer counts from 0 to 23,519. And lastly, the BROM pointer counts from 0 to 29. I encourage you to visualize for yourself why the pointers increment in this fashion. The final question to ask when implementing the first layer is how do the pulses need to be applied? Fortunately, this process is very simple. For the first neuron in each layer, we simply apply a number of P1 to P3 bursts that is equal to the length of the input vector. In the first layer of our neural network, the input vector has 784 elements, so we apply 784 bursts of P1, P2, and P3. This is the first of those bursts. This is the second of those bursts. Then we keep applying the burst as indicated with the dots. Then this is the last of the burst. Then after that burst has completed, we do a burst of the other signals one time. What you just saw calculates the output of one neuron in layer 1. To calculate the entire layer, we must repeat the exact same process for each neuron. Since the first layer has 30 neurons, we must do it for a total of 30 times. So there you have it. We have completely explained how the first layer of our network is to be implemented. We explained how the layer calculator module here would need to have its memory units formatted and how its address generators would need to operate. We also discussed how the pulse generator module would need to output the pulses to drive the layer calculator module. So this here is how the entire feed-forward neural network would be implemented. We just went through the details of how to configure the modules for the first layer. The remaining layers would be configured using the same methodology. Lastly, there's a simple module that returns the largest value written into it from the last layer. To connect the neural network to a computer, we must connect a UART receiver controller to it. To display the results of the network on the 7-segment displays, we must also use the 7-segment controller. Now both the UART controller and the 7-segment controller have been discussed in previous videos, so their Verilog code will not be discussed here. Instead, I will explain the important details at a high level. If you would like the complete code for them, you can purchase the book to get full access to it, and you will also get a much more detailed explanation. The computer will send each flattened image serially over the RX line using the UART protocol. The UART receiver will capture this byte stream and drive its outputs. Those outputs then feed into the receiver RAM interface, which drives the write bus connected directly to the XRAM inside of the Layer 1 calculator module. So there you have it. We have now covered every part of the AI accelerator. We explained the FFN module and how it was implemented using a modular architecture that enables new layers to quickly be developed with simple configurations to the modules. We covered how the UART receiver works, and we covered how the 7-segment works. Next video, I will explain how AI accelerator research is done at the PhD level and how companies and industry are investing in it. If you have any questions, comment below and I'll be sure to answer them. That's all for now, and I'll see you next time.